and you can modify it or make your title known. And my title on Meetup under organizer is organizer may be too strong a word. So super leader, please don't say things like that. So I expect Sam is ready to go. He needs to introduce himself for posterity, and you're off.
Well, just as organizer is too strong of a word, ready is even less strong of a word. But I just wanted to chip in and give a quick update as to what I've been doing in the past year and a half. So my name is Sam Falvo. I am probably best known for um, such um, things as the Kestrel project, also aesthetic programming concepts, things like that. Um, and yeah, for the past year and a half, I've been off doing other things, still trying to keep the Kestrel project up and going. Um, Unfortunately, the Kestrel project itself has I've essentially disintegrated that project after the Raptor engineering folks came out with a project of their own called Kestrel, and in interest to simultaneously avoid legal issues in the future as well as to minimize market confusion, I decided to dissolve the Kestrel project. But I am still working on homebrew computers, especially those that are uh, programmed and or built up from the ground using Forth or Forth-like architectures. And for the longest time, I've been working with the RISC-V architecture, which I do have intentions of continuing to do in the future. But right now, I'm focusing my energy on a new stack architecture that's kind of taken up my imagination at the moment. So let me try sharing my screen, and I will see how this works. I will go with desktop 2 and share that. No, I don't want you there. You go away. All right. So um, basically, it's a fairly conventional bytecode environment at the moment. So I'm going to click into emulator here and going to look into source, and I'm going to click into main.c. And as you can see, I'm not going to really explain in detail what's happening here, but you've got a bunch of words that are working on the data stack. You have a bunch of procedures that are working on the return stack. You have methods of accessing the memory at the byte level instead of full words. You have some illegal opcode handlers that are kind of stubbed out at the moment. Eventually, they'll cause traps. But this is the big thing right here. Like, so it's essentially just a tight loop. And what it does is it will read a byte from the program memory and it will dispatch to a handler based on that byte. So it's a fairly conventional a token, bytecode based interpreter. And as you can see, I have 38 instructions defined. Is there a question? Wasn't sure if I was talking over anything. Okay, so I've got 38 opcodes defined. So it's not exactly a minimal instruction set computer. It started out that way, but then eventually it kind of grew a little bit beyond that, although I am trying desperately to keep it from growing out of proportion. So as I was developing this, so eventually the goal is to get this to run in a hardware-based environment, like off of an FPGA. And let me see if I can, yeah. So this is the FPGA in question. This is the tiny FPGA DX module, which I have quite a number of them in my inventory at the moment. And this is a nice component to target because this is programmable with all open source tooling. You don't need any proprietary developer tools in order to target them, which is really, really quite awesome. So if we go back here and we go into the assembler is written in G4 at the moment. And I'll just scroll all the way down, and you can see basically it is 205 lines of code, and that includes commentary. Using create does to basically describe of the processor. So basically you've got fetch and store memory, which is the full cell-wide instructions. Then I've got fetch byte and store byte. Then I've got basically program flow group here. I've got subroutine call, return from subroutine, conditional and unconditional branches, and so forth. You'll notice that call and unconditional branches, everything here takes an address off the evaluation stack. What is different from my previous stack-based processors is that it is now a proper two-stack architecture. My previous 16-bit processor, the S16X4, which I built the Kestrel 2 using, had only a single stack, and that was the evaluation stack. So for the first time, this is my attempt at building a two-stack processor. And it's got the usual stack manipulators. I've got push and pop for moving data between data and return stacks. Top operators, drop, dupe, swap, over, nip. These are the functions that I use most frequently. And then I've got single bit shifts and rotates. And then I've got sign extend byte, which basically allows you to sign extend a byte into a full cell width. And add subtract, an instruction which isn't strictly needed, but is awfully convenient when you have it on hand, and that's bit clear. That's equivalent to A and not B. I really, and this comes up a lot when you're dealing with graphics, for example. And I really wish that more instructions had that. I'm sorry, more instruction sets had that. And just recently, I added two instructions, fetch register and store register. And that's because I had to move the return stack out of on-chip memory into external memory. And the reason for that is a relatively simple program that I'm working on would have blown I use so many layers of subroutines that it would have destroyed the return stack contents. And needless to say, that leads to software crashing very quickly. I do have a handful of multi-byte operators here as well. I've got 2-byte instructions, which are used to push data onto the return stack, and I also have a set of 3-byte instructions to do the same. There's two variants. This particular variant, this hash comma, or hash comma, as the case may be, that pushes an immediate value onto the stack as is. But this hash IA and hash IA, that's used to push a effective address relative to the instruction address, hence IA. So what this allows you to do is, regardless of where the program is loaded into memory, you always know the address of a variable relative to your instruction. This is especially useful when you're computing effective addresses for subroutine calls and conditional jumps as well. Very, very useful. And as you can see here, for if, neg-if, and then, I use this functionality quite frequently. I've got all the usual begin, again, while, repeat. The only one I haven't implemented yet is until, because I just haven't used it yet, but it's fairly naively defined from this. Numeric constants They're handled interestingly. Basically, if it fits within an 8-bit operand size, we use the immediate uh, operator there to push it onto the stack. If it fits within 16-bit, we use hash hash comma for that. Otherwise, what we do is we'll allocate a cell in program memory and stuff it in there. And what we'll do is when we reference that in the later on in the source code, we'll compute the effective address to it and we'll fetch it from that memory. And through this mechanism right here actually addresses one of the big problems that I had with the original S16X4 architecture that I was building years ago, and actually what motivated me to look into RISC-V so many years ago as well, is program density. The problem with MISC is it's so simple that it wastes a ton of memory. You end up with huge swaths of code space that are just filled with zeros for most applications. So what I wanted to do is I wanted to build an instruction set which put a cap on that amount of wasted space. And this is the mechanism that I came up with. I'm probably not explaining it very well because I'm not terribly organized for this talk, but if anyone wants to continue to learn more about this, feel free to email me. I'm available on the mailing list. And I'll also post my email address in the chat as well after I'm done here. So this is just a very quick walkthrough of the assembler here. Like I said, it's only about 200 lines long. What I'm going to do is show you now a quick what assembled code actually looks like. So this is essentially what the assembled code looks like. Here you can see I'm defining constants for hardware resources in the virtual computer that I'm building. The control port is like a debug thing. It's connected, at least a portion of the pins are connected to LEDs, for example. I have a device called a QIA, or a Q interface adapter. Doesn't actually exist yet, but basically it's like a FIFO interface between the emulator and the fourth environment that I'm running. And basically what I do is I use that to communicate. In this case, I'm building an interface that allows me to send messages to the emulator and receive messages back. And so basically I'm building like a test to make sure that that interface works correctly. So what we're seeing here is what a typical piece of code looks like. I apologize for the red rectangles. It doesn't understand what that is, this website, but basically it's fairly conventional. You know, instead of semicolon, I have RFS, which is the return from subroutine instruction. This relates very closely to what Chuck Moore was talking about back in the 90s called machine forth. And so basically it's kind of a regression back to that, getting back to my roots essentially. And so, yeah, this is kind of what the assembled code looks like. And when we actually try running stuff, which I will try to do now. So if I just run the emulator, you know, as you can see, it's doing something, right? Remember that control port where I said it was attached to LEDs? That's kind of what we're seeing here. And the program code that I'm currently running for that, if I go to firmware, so basically I'm attempting to build a, well, anyone familiar with Plan 9 will immediately recognize the 9P2000 protocol header there. Essentially what I'm doing is I'm refining out that message passing interface between the emulator and the emulated computer. And the idea is the keyboard, mass storage, and the mouse will all be accessible via the 9P protocol through that interface. And so when I build actual hardware, I'm not tied to you know, like if I need to write device drivers or whatever, it allows me to write the device drivers just once, and I can move it essentially as is from the emulated environment into physical hardware. Whereas before, if I wanted to take, if I wanted to build an emulator for my Kestrel 2, for example, it's easy enough to build the processor emulator, but now I also have to build an emulator for the SD card, and I have to emulate the protocol for that, and that includes bug for bug, because the code that I wrote for the Kestrel 2 depends on the bugs that I ran into um, when I was getting it working, right? So, and that just makes things really complicated. So what I wanted to do is I wanted to abstract the I/O out from that, and this allows me to do that. So this is kind of a quick sketch of what I'm currently trying to do. Right now, it's all built in software. The architecture is designed to be, as it currently is, it's designed to be 16 bits wide, but the plan is to widen it to 32 and eventually to 64 bits. And to do so without changing too much of the instruction set architecture. The goal is to have some degree of backward compatibility. Again, primarily because I just don't have the time to go through and just to rehash everything all the time. So I think I have some success in achieving what I want to achieve. You saw the 00FF twice on the code. That's this code right here, which is basically confirming to me that my communication channel to the emulator is actually up and running. So I've at least gotten that far. So yeah, so that's kind of what I've been working on. You'll notice that the project name is no longer Kestrel 1 or Kestrel 2. It's now Fourth Box. And basically, long-term vision, I would like to have some manner of Forth running on it, but also I'd also like to try porting Tripos to it, as well as maybe Project Oberon as well. So those three environments, I think, would be enough to make me happy with the project. That's kind of where I'm at right now, and I'll stop sharing so so that people can actually hear me. I'll eventually let my CPU fan cool off, and hopefully, yeah, I'll be able to make some progress on this. Is there any questions? I see some activity in chat. Let's see here.
What is the nature of your CPU fan that it's so loud?
It's internal to the computer. I don't have an external mic, so what you're hearing is vibration from the fan.
It wasn't that bad. In chat was just that you made an interesting comment about the BIC, B and A and not C, or A and not B, and you were talking about graphic operators, and then later you mentioned a mouse, and it makes me curious about how far you've gotten with doing graphics. You wouldn't happen to be building a GUI, would you? Because there aren't a lot of forces that make it to a GUI. That's kind of a special, point in my mind.
Yes, eventually there will be a GUI, not a terribly sophisticated one. Basically, my target for the graphical interface would, if you're familiar at all with like Commodore 64's version of GEOS, if you're familiar with that interface, that's essentially the level of complexity that I would try to target with for.
That's great. That would be very interesting. I think it would be a lot of fun to have an interactive environment on a very small platform like those FPGAs, like those tiny FPGAs, where you can actually, click and point and do that kind of stuff. I don't know if you're familiar with the One Laptop program for kids.
Yeah, the OLPC. Yeah,
Yeah.
I'm familiar with the existence of the program, but I've never directly used any of the hardware for it.
It just the point is just that you can do an amazing amount of good with next to nothing against real serious hardware costs. you know, maybe it's better to distribute cell phones or something like that. But I think there's an opportunity for really low cost hardware to be used to reach a lot of underserved areas, or just to screw around and have fun with something that's small, but that, you know, can actually present a nice user interaction where you can, you know, play a game of chess or, you know, do something like that, and well, present a visualization of the force stack on a fourth machine on an FPGA. That would be a cool demo. Anyway.
Yeah, yeah. The my personal goal is to just have you know, just a fun computer to hack on. At one time, when the Kestrel project was like in full force, I had a challenge posed to me, which was to use the Kestrel to perform my day-to-day job for 1 week. And he didn't really stipulate how he wanted to do that. And so I came up with a way to kind of cheat in a way. And my approach was to use unencrypted TCP/IP to talk to my, at the time, my MacBook Pro, and use a VNC client. So the idea was to use it as a really, really thin terminal. But I asked him, and he's like, "Yep, that counts." So who knows? I might end up demonstrating, you know, demonstrating the VNC client
for
eventually.
head-mounted displays or portable work, where you want something really lightweight and really low power that can just, you know, connect you back to your main iron in the office while you walk around in the garden.
Oh yeah. Yeah, augmented reality is an area. It's not an area of research that particularly interests me directly, but I can definitely see the value of the research that's being performed into it. I mean, imagine, like I can totally imagine, for example, if someone had a sensor array mounted, you know, somewhere, and you know, you're examining the construction of a home, for example. Instead of imagining placing the beams here, well, what would it look like if we actually, you know, put the floor this high instead of that high, you know, and you're actually interactively building the house, and the CAD system is automatically updating the you know, the blueprints as you're directly you know, manipulating the you know, the subfloor of whatever you're working on. You know, that would be amazing. I think that would be a game changer for that. All right. I think no further questions. So thank you for listening to me to ramble. And who knows, maybe in the future I'll have something a little bit more structured and a little bit more in depth. And I release the floor.
Thank you very much, Sam. It's great to hear from you again. So with further ado, we'll go back to Bill, and not having had enough, he has a second presentation for us today.
There was a question from BB. It was, hand went up. Is that an open question? I guess not. We will go on. Okay, let's see. Test manager.
BB says he was just clapping.
Oh, good. Okay. I'm working.